Hello, and welcome back. In this video, this is the second part of our video series on quadric surfaces. I'll be talking about paraboloids. Now, with ellipsoids, remember with ellipsoids, all three of the basic traces were ellipses. With paraboloids, there's really no way to fit three parabolas together that are all orthogonal to each other. So it doesn't really make sense for all three traces to be parabolas. So that's not quite what defines a paraboloid. Rather, a paraboloid has two of its basic traces being parabolas. Now the third trace, that leaves us open. We can sort of fit this together if the other trace is an ellipse, that generates an elliptic paraboloid, or if the other trace is a hyperbola, and that makes a hyperbolic paraboloid. So this gives us two varieties of paraboloid. Let's take a look. Let's investigate one of these. We're going to investigate an elliptic paraboloid. Now, take a look at this equation. You see an ellipse equation somewhere in here. Yeah, right here, x squared, y squared, constants on the bottom, and both positive. So that is, if I set, say, z equal to 1 here, I get what? 1 equal x squared over 4 plus y squared over 9, and that gives me an ellipse. An ellipse where my x goes between, what, -2 and 2? And my y goes between -3 and 3. Now, if you're questioning where I'm getting the 2 and the -2 from, and the 3 and the -3, make sure you look through chapter 12 or watch those introductory videos I made for this section where I go over how to recognize the form of an ellipse from an equation that looks like this. So that's kind of cool. When z is equal to 1, we get an ellipse. Let's set z equal to 0 and see what we get. Here, well, we got to think about this a little bit. X squared is non-negative, right? Anything squared is non-negative. Y squared is non-negative, and 0 if and only if x is 0 and y is 0. And so the only way for the sum of these to be equal to 0 is if both x and y are 0. So this gives us not a curve, not an ellipse, but rather a point. This is the vertex of our elliptic paraboloid. Let's keep going with this. Let's find another trace. What about when z is -1? What does my surface look like below the xy plane? Well, here I'll get -1 equals x squared over 4 plus y squared over 9. And I've already talked about this. X squared is non-negative, y squared is non-negative, so how could I possibly get a negative? There is no solution to this equation, and hence there is no trace at z equals -1. So that is, when I'm graphing this, my figure, my surface, will not go below the xy plane. It'll just have it'll intersect the xy plane at that point, 0, 0, 0, as I said, but there won't be anything below the xy plane. So let's go ahead and start by just drawing that ellipse at z equal 1. So I'm going to go ahead and put z equal 1 here. And I want to draw an ellipse where the minor axis is along the x-axis, and that goes from -2 to 2, and y goes from -3 to 3. So I'm going to mark those ticks down. Let's see, my y, 1, 2, 3, 1, 2, 3, 1, 2, 1, 2. And I want to draw an ellipse. I don't want to draw it in the x1 plane. I want to move it up here to z equal 1. So one easy way to do that is to just copy my x and y axes, but at z equal 1. So I'm just going to move up the origin, and then I'm going to draw it up here instead. So I should do dotted lines, because this isn't, it's not the actual axes, and it's not part of the figure. So I'll draw dotted lines here. That one was parallel to the y, so that was the y shifted up. How about x? Oh, that's about right. And here's my x-axis, shifted upward to z equal 1. All right, so there's, my axis shifted up. So I want to go between 2 and -2 in the x direction. Right, so here's that's y, 3 and -3 in the y direction, so maybe I'll do those. So here I am up here at z equal 1, that's y equal 3, z equal 1, x equals 0. Here I am at -3. And then I want to do the same thing here for x equal 2. Notice I'm going to intersect with the copied version of the x-axis here. -2 there. And now I can draw my ellipse. So I'm going to have an ellipse here. I know that this part of the ellipse I'm not going to be able to see from this first octant here. So I'm going to draw dashed lines for that. Here it is. There's my ellipse. I'm not going to be able to see this from my vantage point. Ellipse is going around like this, right? It's in perspective, so it looks a little bit wonky. That's okay. So there's my ellipse now at z equal 1. All right, it's hard to see how to fill out this surface until we look at some other traces. So let's say I set z equal to, oh, I already did z equal to things. How about x equal to 0? Let's try setting x equal to 0 and see what we get out. We're going to get what? Z equal, this term is going to go away, y squared over 9. So that's a parabola. And I can pick out a couple points on the parabola, right? If y is 3, then z will be 1. So x is 0. If y is 3, z is 1. So I'm just keeping in mind these points. If y is -3, z will also be 1. Just so I can remember with the parabola, it's nice to get 2 other points in there besides the vertex. This vertex will be at 0, 0, 0. Just so we can get the general shape of it, how wide or how tight it is. And then let's set y equal to 0. And that's going to give me z equal x squared over 4. And my points here would be what? 2, 0, 1. And -2, 0, 1. And so I'm going to go ahead and draw these parabolas. This one is going to be in the yz plane. This one is going to be in the xz plane. So the yz plane, I have this parabola where when y is 3, my z is 1. Oh, I already have that point marked. Interesting. I'm going to draw this one in red. So I get this parabola in the yz plane. I should be able to see all of it. I can kind of continue on from here, right? I know the general shape of a parabola. So it's okay to just kind of freehand past that one point, but it's good to have just a couple points to start with. So there's that parabola. Notice how the ellipse goes. That kind of determines the bounds in the y direction of my parabola. Or rather, the parabola determines the bounds in the y direction for the ellipse. Either way is fine. And then in the xz plane, that was when y is equal to 0, I have this parabola, z equal x squared over 4. So when x is 2, my z is 1. This is coming at us. Watch out. Just kidding. But this is coming at us, and then this one is going behind us. I'm going to draw dotted lines here. So hopefully this is starting to come together. What we have is sort of like a ball shape with a vertex on the xy plane. So let's see. I could draw, so what happens when I go higher in the z direction? The bounds for these parabolas are determining my bounds for the ellipse. So what we're going to get are wider ellipses up here. Can you imagine that? Around like this. We get wider and wider as I get really close here. I'm going to get tighter and tighter ellipses. And we can see that if we say set z equal to 2. Let's just work it out. Set z equal to 2. What we'll end up with is what? 2 equal x squared over 4. That looks like lambda. X squared over 4 plus y squared over 9. And this isn't the standard form for an ellipse, so what I need to do is divide everything by 2. 1 equal x squared over 8 plus y squared over 18. So now my x goes between negative square root of 8, so a little bit bigger than 2, or a little bit to the left of negative 2, and square root of 8 there. And my y, so that's x, will be here, and then y is going to be between negative square root of 18 and square root of 18. So again, a little bit bigger in the y. So it widens. This should really be inclusive, I think. And so that's why we see this widening effect. As I increase z, the radius or the axes of my ellipse will also increase. All right, let's jump to, so that pretty much does it for the elliptic paraboloid. I'm just going to jump to a interactive figure here. Let me change the scene. Oops, I don't want to see that one yet. That one. So we looked at plane's parallel to the xy plane there, I'm going to just get a point. If I bring it up, that's where I see my ellipses. They get bigger as I go up in the z direction. My y, let's look at xz traces. I get parabolas. And then if I look at yz traces, again, I get parabolas. So two of the basic traces are parabolas, and then the other trace is ellipses. And you might imagine what happens if I say switch x and z here. If this was, say, x equals z squared over 16 plus y squared over 4, something like that, what would that look like? Notice here the z is determining the direction that this, the orientation of this elliptic paraboloid. It's opening upward. So if I switch the x and the z, it's now going to open upward along the x-axis. So it'll be tipped on its side, opening like that. If I swapped the y and the z, it'd be opening upward in the y direction. So switching variables, we also want to keep that in mind. What happens if we switch these variables around? How does it change? It's just going to determine the orientation of it. And so if you follow the steps that I just worked through, I'll jump back to my scene. These steps we just worked through, if you do this every time, this will give you the idea of how to graph it. You don't have to remember. You can work out the orientation just by looking at the traces. Another reason why the traces are so important. All right, so there was one other type of paraboloid, and of course, right, it doesn't have to be 4 and 9 here. I think the one we just looked at in the interactive figure wasn't quite that. In general, this is just, some A, and this is some B. And then we can work through these steps to determine what it looks like. Parabolas there, and ellipses there. So let's take a look now at hyperbolic paraboloids. Now, instead of ellipses parallel to the xy plane, I'm going to get hyperbolas. How can I recognize that? Well, what if I set z equal to 1? I'll get 1 equal x squared over 4 minus y squared over 4. And I should recognize that as a hyperbola. And if you don't, make sure to read through chapter 12 again or watch those videos that I made. So this is hyperbola. When I see a hyperbola, I like to pick out what are my slant asymptotes and what's the orientation of it. So my slant asymptotes here, remember I get that, that's the ratio of my coefficients here, or rather 1 over the coefficients. So right, square root of 4 is 2, square root of 4 is 2, 2 over 2 is 1. So my slant asymptotes are y equal plus or minus x. And then the intersections, what's my orientation? Well, if I set y equal to 0, I get 2 or negative 2 out for x. So that means this intersects the x-axis. So these intersect the x-axis, and that determines the orientation. If I set, let's keep going, let's find some other traces in the x parallel to the xy plane. If I set z equal to 0, what do I get? I get 0 equal x squared over 4 minus y squared over 4. All right, well, I can kind of solve that out. That doesn't have the right form. I don't recognize that as anything, but I can solve that. I can do a little algebra here. I get what? I can cancel the 4's off. I get x squared equals y squared. Careful here, you might be tempted to say x equals y by taking square roots on both sides. Remember, though, the square root function is not a perfect inverse. You get the plus or minus. So what this actually tells me is that y is equal to plus or minus x. And so that then is 2 intersecting lines. So my curve here, my xy trace, is 2 intersecting lines. And these are the slopes. The slopes are 1, intersecting lines. So as I mentioned in a previous video, that's sort of a degenerate form of a hyperbola, is 2 intersecting lines. Here I'll set z equal to negative 1, and let's see what happens there. I get negative 1 equals x squared over 4 minus y squared over 4. Again, this doesn't have the right form. I need a positive 1 over here, so I'm going to multiply everything through by negative 1, and that's going to have the effect of changing the negative, put the negative on the x, and make y positive. So I'll write it like this. 1 equal y squared over 4 minus x squared over 4. And again, that's a hyperbola. My asymptotes, my slant asymptotes, is, again, y equals plus or minus x. Still 2 over 2. But this time, if I set y equal to 0, there's no x's that satisfy that, so it doesn't intersect the x-axis. But if I set x equal to 0, I get plus or minus 2 for y, and so it intersects the y-axis. So this one intersects the y-axis. Okay, so for drawing this one, I'm not going to draw it all in detail. I just want to sort of keep that in mind. I'm just going to draw those traces. So at z equal 1, here I am at z equal 1, equal negative 1. I'm just going to make sure I can see this. Yep, okay, good. So up here, I'm going to get hyperbolas that intersect the x-axis. That's going to be here. So I'm going to get hyperbolas that look like this. I'm freehanding this. I'm not doing this in super detail because this is actually a really hard surface to draw. I encourage you to try. I've tried it enough times to know that I just cannot get a nice looking figure here. And then at negative 1, I have hyperbolas going in the other direction. So something like this. And then at y equals 0, we get these intersecting lines. So it's not clear right now how exactly that's going to fit into the rest of it. And then we know this is a paraboloid, so when I do other traces, so if I say set x equal to 0, let's see what I get out. I get z equal negative y squared over 4. So I get parabolas that are opening downward. And let's see if I set y equal to 0. So that's in the yz plane. My parabolas are going to be opening downward. If I set y equal to 0, so in the xz plane, I'm going to get z equal x squared over 4 positive. So those are going to be opening upward. So both of these are parabolas. They have different orientations. So when I look at it, my xz plane opening up, yz plane opening down, strike that, reverse it. But it switches orientation when I look at it from those orthogonal sides. What if I set x equal to like 1? Or let's actually set x equal to 2. I'm going to do that one. Set x equal to 2. I'm going to get a 4 here, so I'm going to get z equal 1 minus y squared over 4. So this has now been shifted up. It's this guy, but shifted up 1. So as I move closer to me, x equal to 2, right, coming forward in the x, my parabolas are going to shift upward. If I do, like, let's say, set x equal to negative 2, the same thing is going to happen because it's going to be squared. It's also going to be shifted up. So as I move forward and backward, I'm going to get parabolas that are shifting upwards and opening downward. I can look if I set y equal to 2 or negative 2. These are going to shift these upward facing parabolas downward as I move in either direction along the y. So here we're going to get parabolas opening upward, and then they're going to shift down. So it's not immediately clear what this is going to look like, and I'm not going to try and draw it exactly. So I'm going to jump to an interactive figure. There's my elliptic paraboloid again. Here is my hyperbolic paraboloid. So let's try and let's try and find those traces in this to see how we could have put this together. So I'll start with my z traces as I did with the equation. So that's at z equal 1. I get this hyperboloid or hyperbola that intersects the x-axis. Well, x-axis shifted up, right? That's the orientation there. And then z equal to negative 1 going down. See how they change direction. And those are not parabolas. They might look like parabolas, but those are not parabolas. Those are hyperbolas. We can recognize that from the slant asymptotes. As they move down further, these are going to get a little bit tighter. So those were those traces. When I look at the xz plane, I should see a parabola. And let's see, as I move the y to the right or the left, this should shift downward. Right? Shifting down. It's the same parabola, just shifted down. Same thing if I go in the other direction. And then lastly, in the yz plane, I get parabolas that are opening downward. And as I change my x, this is going to shift up. Pretty cool, right? And so that is a hyperbolic paraboloid. Again, difficult one to draw. This is like a, you can think of this as like a saddle type shape, something like that. difficult to draw, but again, that's not the point, is to draw this faithfully, but rather be able to recognize what the surface looks like from the equation and the reverse of that. Being able to look at a surface and say, oh, that's a hyperbolic paraboloid. I know it has some form that looks like this. That one that we're looking at here isn't quite the one we just were looking at, right? It's changed a little bit. Again, we just generally have constants down here that are determining what the slant asymptotes of that hyperbola are, what the intersects are, as well as the shape of the parabolas in this. So changing those constants moves this around. Again, we might want to think, what if I swapped x for z here? So what if it were x equals z squared minus y squared over 4? What's that going to do? How do we work our way through, the logic of that? Well, if I had x over here, one way to think about this is, are these parabolas? My parabolas are going to be in a different trace this time. It's going to have the effect of flipping this onto the x-axis, right? Take this whole thing and kind of flip it, turn it 90 degrees, counterclockwise would be that effect. Or if I swap y and z, I'm going to effect of flipping this onto the y-axis, right? So it's just going to change the orientation just like it did before. All right, so that was paraboloids. That is it for this video. In the next video, we're going to talk about hyperboloids. And if you see the pattern here, 2 of the traces are going to be hyperbolas, and the third one is going to be open. Well, we'll see. I'll see you there.